Welcome to Spring LIB.
So starting off with a particle and mass, you have two energy equations we're going to use. They're both equivalent. First is that energy equals kinetic energy, total energy equals kinetic energy plus rest mass energy, EC squared. And the other is that E squared, same energy, total energy, equals PC squared momentum energy plus rest mass energy mc squared whole squared. Okay, so from here, PC squared is just E squared minus mc squared whole squared. And we substitute E in from here. And so PC squared is just KE plus mc squared whole squared minus mc squared whole squared. Okay, let's move on to the next page. We have that KE plus mc squared would be equal to, from here, just pulling out the mc squared whole squared term to the other side. So that should be equal to the square root. You have to take a square root because this whole term is in a square. Square root of p squared c squared plus m squared c to the fourth. Just writing that out. Okay. Therefore, for a mass particle with mass Ke is square root of p squared c squared plus m squared c to the fourth minus mc squared. So that's your equation, and that's what we're plotting here in this plot on the left-hand side for mass. Now, there are two regimes here, the low momentum and the high momentum regime, and so this p squared over 2m is for the classical regime, and this pc minus ec squared is for ultra-relativistic or very fast motions or high momentum regime. So let's actually work that out to get a better understanding of what these plots are telling us, or what this plot is telling us. So in the low momentum case, and let me actually use a different color here. Low momentum, you have that Ke is, okay, I'm just going to rewrite this in a different form that will make it easier to use a binomial expansion. Is equal to mc squared plus, again, just rewriting mc squared times 1 plus pc over mc squared whole squared to the 1/2. And this is because you can take mc squared as the common inside of the square root, and then you have to divide by mc squared for both terms. And so this thing goes out, but so this thing becomes 1, and the p squared c squared term gets divided by mc squared in this way. And so this is just an algebraic trick. And the reason we're doing this is because we want to use the binomial expansion. So this would be appendix A, from the appendix A6. And A6 says that 1 plus x raised to the nth power is approximately 1 plus n to the x when x is much, much less than 1, which is the case here, right? Here, pc is much, much less than mc squared, meaning the momentum energy or energy from velocity is much, much less than your rest mass energy. And so this means that 1 plus pc over mc squared whole squared to the 1/2. So n is 1/2 here, and x is this square term in this term squared. So this should be equal. This should be approximately 1 plus pc over mc squared times 1/2, and this 1/2 came from the exponent and or square root of 1, right? So therefore, what we get is that Ke equals negative mc squared plus mc squared times 1 plus 1/2 pc over mc squared, right? Well, I guess approximately, but it is a very good approximation at lower momentum. And so you note that the mc squares, like this term and this term cancel, and what you end up with, and here, oh, also forgot to write square out here, right? So your mc square cancels with this mc squared, and the c square on the numerator cancels. The c square on the numerator cancels with the c squared remaining on the denominator. What you end up with here is that Ke is just p squared over 2m, okay, which is the classical relationship for kinetic energy and momentum. So it would be this regime. And now for the high mass, the high momentum regime. Let's use a different color here. For high momentum, you have that momentum energy is actually much less than greater than rest mass energy, and so this means that Ke is approximately, again, you have negative mc squared plus you had the whole term in here of p squared c squared plus m squared c to the fourth. This term will dominate over that, and so what we get here is that this is just square root of p squared c squared, because mc squared is small. And so this comes out to be negative mc squared plus pc, and that's what we get here in the higher momentum regime. And finally, for no mass, so mass equals 0. So in the case of virtual particles like photons and neutrinos, you have that energy is just momentum energy, because rest mass energy is 0, mc squared is 0, and so all of your energy is kinetic. So Ke is pc, so there's a linear correlation between kinetic energy and momentum energy. So the higher the momentum gets, the higher kinetic energy gets, and there's no difference between the low and high momentum regime in this case. And that's it.